Okay, welcome everybody back to Orlando Machine Learning and Data Scientists series on end-to-end machine learning. My name is Ron Bergeron, and Ricardo Serrano is with us, another co-host and organizer of the meetup group. Today is the 6th session in the full series, and we will find out later from Ricardo and through the quick intro here that we're going to be focusing on the SciKit Learn library and tools around that. Our objectives in this overall project are just for the meetup group to do a project that introduces the concept of a full life cycle of a machine learning project, and we'll see some more of those. We've already done our introductions prior so that our folks that don't want to come off online and be on the video don't have to be. And I've also posted this information about Discord and some of the other links in the chat session. So feel free to copy those out of the chat window and grab the links. We have links there for the meetup group, the YouTube channel, Discord, the GitHub repository, and the Google Drive location that we're using during this series. We are basing this series on one of the Kaggle data sets for credit card fraud detection. It's a very commonly used intro data set, and it's very well refined, and so there wasn't a lot of cleanup on it, and it gives us a good starting point without having to do into the a lot of the data janitorial work prior to starting out the project. Overall, in the timeline of a full machine learning lifecycle, we have covered these first two bubbles, the business data understanding and the data preparation, and we're now moving into the build section in this first bubble, the model engineering slash the next step will be evaluation. But today's will focus on our first steps of creating our first model, and we are going to be primarily revolving it around the SciKit Learn library. And as Ricardo mentioned a little in the pre-session here, so we learned a little bit of the history of SciKit Learn when we were preparing for this session, and it actually predates pandas, which is one of the key things that is interesting about it. Oftentimes when we've been working with it, there's some little idiosyncrasies in interacting with the pandas data frames, and we always wonder, why is that? And now we understand in our history of preparing for this is it predates pandas. So where it was more readily integrated with NumPy and SciPy and Matplotlib, because those existed at the time SciKit Learn was being started, pandas didn't exist. So we understand now some of those things. But this is a full-fledged library. It's open source, and the license is, I believe, a BSD license. So it's available for both personal and commercial use as open source. So it's a great library to use in general in machine learning to not worry about trampling on any licensing issues, especially if you're going to get into some commercial applications. And it's also a great learning library. Overall, SciKit Learn has these groups of functionality throughout the library. It covers the main areas of machine learning, the classification and clustering areas, as well as regression. And then it has a section of things for dimensionality reduction. This is really important when you have lots and lots of factors come into play. I know Ricardo and I were on a project with the foster care system where, you start out the project, and this happens in a lot of commercial settings, is the idea that people come to you with just has so many potential possible factors, it becomes a bit overwhelming. You have to really work to reduce those down to what are the important factors that actually contain information that the model can learn off of. But today's session is actually going to end up focusing in the classification area, because that's where this fraud detection problem really resides. It's classification of, you're trying to decide if a transaction is fraudulent or not. So that's a clear binary classification situation, and that's where the model or the rest of the focus of today's session and this early model that we've developed will be focused on. Ricardo is going to actually be taking over and doing the section on this. And so let's jump right in and get going. Ricardo?
Yeah, let's do this, right?
Let's do this.
Let's go to modeling, the fun part. All right. So let me share my screen here. Okay, thanks for the introduction, Ron. I think I need some
There
permission.
you go. I just turned it on. You should be able to share. Sorry about that.
Yeah, Ron runs a tight ship, you know. Here.
But unfortunately, we had a little issue
Yeah,
several sessions ago with
we
the
have some
timer that got on
we have some
our session,
yeah,
so we have to
we have
lock
some
things down.
jokers, you know, around. Yeah. Okay. So I want to begin first, you know, before delving into, you know, the modeling part. I have a question for the members that are joining us today. And the question is, put in the chat, if you have never, you know, if you have never, you know, heard about SciKit Learn, put a 0 in the chat. You know, this is new to me. I have no idea, you know, what SciKit Learn is or what you're talking about. Okay, John, good. Okay, so I assume that, okay, here we go. Mike, also, good. Okay, so I'm assuming that, how many are we here?
We have
We're 7 minus 2, 5. So around half an audience, you know, they, you know, haven't heard about SciKit Learn. Okay, so as Ron mentioned, SciKit Learn, at least for Python, is the de facto library for machine learning model. Okay, it's an open source. You know, it doesn't cost anything to use it, and also is very well maintained, well developed. Like in the slide said, you know, it was a project that started in the Google Summer Code in 2007, and yeah, you know, it caught fire, like you know, the good things like pandas, for example, and also it's a good tidbit of knowledge that SciKit Learn predated pandas. Pandas was released in 2010, and SciKit Learn is before that, 2007. So you will see certain weird things that are happening that you have to transform them, you know, to transform them to a data frame. Okay, so with that, you know, basic introduction, because this is a classification model, right? And let me show again the let me show again that chart, okay? Because it says a lot. So we are in the same page. Okay. So in that bubble, right? The bubble of a classification, and this is a classification problem, you will see that it gives you like a path, right? You know, from the start, it gives you like a path. And then if you're in the classification area, one of the things that the SciKit Learn, you know, recommends is that if you have more than 100,000 samples, and our data set, you know, in full display is about 1.2 million, we're just sampling it right now for efficiency purposes. It caught my attention that if it's more than one, then you go to this model, which is the SGD classifier. SGD stands for Stochastic Gradient Descent classifier. And what it does, you know, in a nutshell, not to get, you know, too, you know, deep in the weeds, what it does is that these classifiers models, what they do is that they use a metric in several iterations to try to better their performance, changing some of the weights of those predictors. Okay, so imagine that we have like a linear, let's say like a linear regression, and the weights are the coefficients of the linear regression. So what the model is going to do is, instead of in a formula trying to minimize the errors, what it's going to do it is iteratively, like a simulation. And in that SGD classifier, if you go to the SciKit Learn documents, okay, SGD classifier, what you will see is that this is not one model, okay? This is a combination of different models depending on the arguments. So you kind of create your own model depending on, you know, what is the function that you are doing. And you can then tailor this SGD classifier to a logistic regression, which is the model that we're going to use as a baseline. Why are we using logistic regression? Well, two things. First of all, it's a traditional model like linear regression, but for classification. Okay, so you have zeros and one, you know, your output is bounded. And also, it's a model that is kind of a white box. So it's easy to explain because what it's going to do is assign certain weights to your predictors, and then you will see which are the ones that had more weights, which relates to the variable importance of that model. So for example, in this case, we have a predictor called amount, the amount of the transaction, right? So if that predictor has a significant weight, you know, a significant estimate of the coefficient, then we can assume that that model is, you know, that predictor is important to the prediction of the outcome, if it's fraud or no fraud. Okay, so just trying to give you like a, you know, like a bird's view of what, you know, we're going to be doing. Okay, please, if you have any questions, you know, just, you know, put it in the chat, or just say it. Okay, so logistic regression. In logistic regression, let me see if I have something here. Okay, let me see. Okay, so in the logistic regression, what we're doing is, you know, it's a regression, but it has certain, you know, peculiarities. Okay, we know that in linear regression, which is predicting a continuous variable, we have a function called, you know, like y, which is the response, equal to certain predictors, right? You know, the sum or the subtracting of certain predictors. In logistic regression, we have the same kind of formula, but instead of the y is transformed to this function. Okay, let me see if I can put it here. It's this function here. I don't know if you can see my my mouse. Okay, and what is that called? That function, what is called, is a logit. Okay, so in other words, we are transforming the output of the predictors, we are transforming into a logit that is going to have this kind of function. Okay, it's going to be a curve, like a sigmoid curve, but it's going to be bounded by 0 and 1. Why? Because it translates in what is called a probability. And the probability, by definition, is a number between 0 and 1, and is how probable is the outcome or how improbable is the outcome. The more near to 1, the outcome is probable. The more near to 0, the outcome is improbable. So it gives you that, you know, spectrum of probabilities instead of the linear regression, which gives you continuous numbers. Okay, so what are the assumptions? Every model has certain assumptions that you should be aware, because those assumptions, if they are not validated by the model, then on the long run, that model is going to be unstable and is going to be prone to give you problems, you know, in the long run, especially in the deployment. So one of the things that the logistic regression assumes is that the response variable is binary or dichotomous. In other words, it only has two states, 0 and 1, true or false, fraud, no fraud. Okay, and the observations or independent variables have very little or no multicollinearity, and that's something that also it matches the linear regression. In other words, we are trying to get predictors that they are not related within themselves, because that then provoke a problem that is called inflation. In other words, they tend to grow, the estimate tends to grow because of that interaction between those predictors. There are no extreme outliers. There's a linear relationship between the predictors, but instead of the outcome is the log odds of the outcome. And the log odds is the log of the odds ratio, which is the probability divided by the 1 minus the probability of that outcome. Okay, And usually you need a larger sample, not to get, extreme bias and get more reliable products. The larger the sample, the better. And in this case, we have no problem because the data set is large enough. It's about, the full set is about 1.2 million records. Right now, we're using only half of it, just for, execution. The execution is not that high. So let's begin. This is the notebook that is going to be also in the repo, but it's in the Google Lab link that Ron showed you. So the first thing that I have to do here, okay, let me see if I can connect to a runtime. Okay, hosted runtime. All right. Let's wait for the connection. Okay, and then I have to install this library. It's called Seaborn. It's for visualization. But after the version 12.0, they did a couple of changes, in the arguments and also in the structure of certain, functions that is compatible with previous. So I'm using one that is kind of near to the version 12 to assure compatibility. So the next thing that we're going to do is import some libraries. And if you have been following us, there's some libraries that are kind of the standard, which are the pandas library for data frames, the NumPy for the calculations, the matplotlib, which is the basic library for visualization in Python, and then the Seaborn, which is on top matplotlib to create nice looking visualizations, and also is kind of a wrapper. In other words, you don't have to code too much in matplotlib to get a bar chart or a line plot, etc. I'm going to try to minimize the warnings. That Python is always warning us about something. Okay, set copy, whatever, and then the parameters for the figure size of the visualization. So let's run that. Okay, we should have no problem there. Let's check that the version of the Seaborn is 11.2, because, if it jumps to 12, things can break. And now we're going to import some of the SciKit Learn libraries. Okay, the first one is going to be make pipeline, and I'm going to discuss that when we go to the modeling. But then also we're going to import something called standard scaler. And standard scaler here is important because for logistic regression, as for linear regression, you need to standardize your predictors, okay? So for example, if you have a predictor that is, from 0 to 10, for example, okay? It's like a level, right? 0 to 10. And then you have another predictor that is 0 to 10,000. That difference in scaling, in magnitude, is going to affect the performance of the model. So in other words, we have to get them into a uniform scaling, which is, in this case, the standard scale is going to transform them into a mean 0 and a standard deviation of 1. All the predictors, which are going to be numeric, of course, right? And we have done this with the feature engineering. Then we're going to import also something called train test split. Why? Because when you are modeling, you want to split your data set, your basic data set, into training and test. And what we're going to do is modeling on the train and then validate that output, validated to a test. Okay, so we don't overfit our model. All right, and then we're going to get that model with new data to get the last final metric to see if our model is a good model or not in terms of overfitting metrics, etc. Then we're going to use the logistic regression model, and then we're going to use some metrics. We can use accuracy, we can use ROC, okay, which is the one that we're going to be checking out, and we're going to define what is that. We're going to do a confusion matrix, very important, because in the confusion matrix, you will see how well your model not only hits the true positive and true negatives, but also the false positives and false negatives, which in this case is very important, because we want to make sure that our model catches the fraudulent transactions, which is in the minority level of the whole set. Okay, right now it's around 0.005. It's a very highly imbalanced data set. All right. Let's mount the Google Drive. Okay, it's going to ask me, certain things here. Okay, I think we have shown this before. And then we're going to be reading our train and test data set. Okay. And this train and test data set already has all the features that we have been talking in the previous sessions, and is ready, almost ready for modeling. The only thing that we're going to do is scaling that data set, which is not in the feature engineer process. Okay, so we're going to read our training data set, already encoded, already with the features, the distance feature that Ron discussed last time, other features that we have added, etc. And right now, our training data set has 648,000 plus observations, which is pretty sizable, with 38 columns, okay? From amount, gender, city population, our target is fraud, and so forth. Okay, and then the info, just to make sure that everything is numeric. Remember, logistic regression needs numeric data, etc. If you have a categorical an object, you have to convert it to the numeric. All right. And then our test data set, which is the test data set is the one that we, isolate from the train. Why? Because we don't have any, we don't want any data leakage. So the test data set, we're going to use it only at the end. When you have the model already trained and validated, then you're going to use this test data set. All right. But we have to do the same process for the test data set that we didn't train data set, because they have to be equal. They have to have the same columns and the same data types. Right. Okay, we read it, and we have around 55,000, more or less 556,000. Good. All right, we got the info. Okay. Okay, any comments or questions so far? Are we good? We're following the process? We're good? Okay, so let's continue. Okay, there's a comment in the chat. Okay, good. All right. So before doing that train test split that I discussed, briefly in the import, the libraries, we have to first split the data set into the predictors and the response. Okay, so we're going to create an object called uppercase X, which is the data frame that is going to have all the predictors. So in other words, we're going to drop, if you're familiar with Python and with pandas, we're going to drop from the trained data set, we're going to drop the target. Okay, so that X object, that X data frame is going to have only the predictors. And then the lowercase y is going to have the target. All right, so this is the first step ongoing splitting our data, right? And just to make sure that we're doing it all right, right? We're going to use shape, the shape argument to check. Okay, we have the same number of rows, good, but in X we have 37 columns. Remember that it was 38, right, before, and then so we don't have that target, and then in the target we only have one. Okay, one column with the target. Now we are ready now to train, split our data set into training and test sets. And this is the formula. You're going to create 4 objects here. Okay. X train, which is going to be about 80%. I'm going to explain why I know that it's 80%. 80% of the train of the original train data set is going to be in X train. We're going to have Y train, which is the response for the X train. Then 20% is going to be then the converted into the X test set. And that's the one that we're going to be using with the training model to try to see if our model doesn't overfit and it kind of generalizes. In other words, we want a model that generalizes because there's going to be coming always new data. If you have a very good model, but then when you apply it to new data, you get a very bad metric, that means that your model is overfitting, and that model is not good. Okay, you have to get to a place where you generalize. You get a model that generalizes, that can accept different types of data, and then run it to the model and get at least that as good as a metric as the train data set. Okay, so we're going to use the train test split. Okay, I'm going to split the uppercase X, lowercase y. We're going to use a chunk of that data set for the test size, which is 0.2. That's 20%. That's what I told you. I know that is 80% train, 20% test, because I'm using that argument. And also, we're going to use a random number for reproducibility, to reproduce this, if we run it again. Then there's another argument that is important here, because remember that our class is highly imbalanced. And what I mean is that there is a lot of transactions that are legit, okay? Around 99.4% of the transactions in this data set are legit. So we are dealing with a very high imbalance, and to get a good measurement from the train and the test set, we have to make sure that the distribution of that target is the same for the train and the test data set. So we use that, it's called stratify, it's a stratified sampling. We use stratify, and we stratify by the target, by Y. And you will see the result, okay? So let's run it. Let me see, train split not defined. Okay, let me run again this. Maybe I didn't run it. Yep, that's what happened. Okay, forgot to run the import of the SciKit Learns. But it's good because sometimes, you get this type of error and you say, what the heck? Okay, so now we're good. So now let's do another check, okay, on the dimensions of those X train, X test, Y train, and Y test. And as you can see, you see that there's a split, right, between the train set, which was this number, right? Now it's split into two, right? 80% on the X train, 20% on the X test. And then we have the columns for the predictors. And also we have our test for Y train and Y test. So everything looks very good. Now, for the stratify, let's check what is the distribution between the target, the Y train target for the train, and the Y test, the test target in the test. Okay, so we run it and we see that this is the distribution for the train and for the test. And you see that basically they are identical. Just a couple of decimals that are off, but that's okay. You're not going to get a perfect number here. But the distribution is basically the same. All right, so now we are ready to apply those data sets, now use them for our first step of modeling. And the first step, remember what I told you about that function made pipeline? So what SciKit Learn developers have done, they have built this function made pipeline to combine some pre-processing that the model needs to the model, okay? So it combines, usually you're going to see in articles, you're going to see that there's some pre-processing. For example, there's going to be a standard scalar applied to the X train and the X test, maybe one hot encoding and so forth, okay? Whatever pre-processing you need so the model can ingest that data set. But with make pipeline, it's really very simple, okay? Because what you do is that the arguments that make pipeline needs is the preprocessor okay? And then at the end, the model. So you got everything combined in just one instruction. So to instantiate, what is called instantiate the logistic regression, we're going to make use of the pipeline, and the only preprocessing that we need right now, because we already done it with the feature engineering, is standard scaler, okay? Scaling those predictors so they have the same scaling, all right? And then when we instantiate, we call it, you can call it anything. Yeah, but I call it log reg, just to make sure that I know that it's logistic regression. And then we're going to fit the model. Okay, so let's run this. And we're going to do it, if we have time, we can come back again and do it with some changes in the parameters of the logistic regression. But right now, we're going to do it with the default parameters. Okay, so let's go. Let's instantiate, do the standard scaling at the same time, and then fit the model, right? Okay, let's see if it does what it's supposed to do. It's taking a little bit of time because remember, there are about 646,000 observations that we're dealing with. Okay, a little bit less, 80% of that. Okay, so we have now our object, right? The log reg object, and it consists of a pipeline. It's telling you it's going to be a pipeline or a standard scaler first, and then apply the logistic regression. So what can we do with log reg? Well, the first thing that we can do is make predictions, right? So what you do is that in the log reg, you do with the function called predict, you apply predict, but instead of the X train, now you're going to apply predict to the X test, the one that we separated from the 80%, the last 20%, to validate our model, to be used as something as a new data, which is not new because it's part of the training set, but it's just a validation process, okay? And we're going to create YPred to save those predictions. And we're going to run what is called the ROC-AUC score. Just take it, by faith right now, the ROC-AUC score, but I explain later graphically, what this means, okay? So let's see how well this train logistic regression looks with the X dataset. Okay, so right now we have a measurement, just a measurement of 0.663, okay? Which is really what it's telling you is that the model can explain around 0.663 in terms of the, the true positive, the true negatives, the false positive, and the false negatives. And you're going to visualize it in a confusion matrix, okay? So let's go to the confusion matrix. Before going to the confusion matrix, let me show you what is a confusion matrix, right? Okay, so let me go here. Okay, let me see if I can bring one of the images that I had in my original notebook, okay? This is a confusion matrix, right? So the output of our results is going to be presented in four quadrants. The actual quadrant is going to be the actual values of your of your data set. In this case, the X data set, and it's going to be divided between the positive and the negative. And it doesn't matter. Right now positive is 0 and negative is 1. Then we're going to then do a crossover, right? A cross tabulation with the predicted. And for example, if the predicted is positive and the actual is positive, in this case 0, that means that there's no fraudulent transaction, the transaction is not fraudulent, then you're going to have this number as true positive. And we want that number to be similar to these two numbers here. Then the true negatives are going to be the ones that the actual is a fraudulent transaction and the model predicted a fraudulent transaction. So those are going to be the true negative. The ones that we want to see how the model predicts is the false positive as false negative. And in this case, for example, false positive is going to be that is an actual fraudulent transaction, but the model did not catch it. Okay, the model said that it was not fraudulent. So that's going to be in this quadrant. And then the opposite, right? The opposite side of the coin. The transaction was not fraudulent, but then the model predicted that it was fraudulent. And those are associated with what is called type 1 and type 2 errors. Okay. So let's go back, right, to our model and see how the confusion matrix, reacts here. Okay, so when we run it, I run it to 4. Let me run it to 3, okay, to see more or less if we get rid of those notations. It's still not great, okay, because this is not 1, this is not 0. But as you can see from these numbers, okay, this absolute values, we get here now some percentage because we are normalizing that confusion matrix. So what is saying here is that from this row, right, if you total this row, let's say 506, 243, 45, 45, you get 751, for example. That's going to be the denominator. So from 1771, okay, you're going to get a proportion of, in this case, let me see, in this case, true negatives. Let me see if I can run this. This one is a little more clear. Okay, we have the same numbers, right? So we have, in this confusion matrix, we have the actual, but the actual is not at the top, it's to the left. And then we have the predicted. So we said that the 0 zeros are the true positives, right? 0, 0. So right now, the true positives are not doing that bad. It's around, convergence or around 0.9997, almost 1, all right? And in the true negatives, right? True negatives, we have 0.3262, which is not bad, not that great, okay? In other words, from half of those transactions that are, fraudulent, we're just cashing around 33% of them. The other ones we're not catching, okay? Because there is a dissonance between what the model is predicting and the actual, okay? Everybody follows me here? Okay, good. Good, okay. So let's see, now that we have a model, right? Let's see what is the coefficients of this model. So the coefficients are going to be kind of the weights of the model, assigned to each of the predictors. So remember, because SciKit Learn doesn't, it didn't consider pandas in their development because panda was not, there. Usually you have to convert the NumPy arrays converted to the data frames. So in this case, for example, the log red coefficients, which is, in this object from the model, is going to be an array. So you have to change it, okay, here to a list, and then combine it with the name of the features. So that's what basically this cell is doing. So let's run it. Okay, let's also run, let's change the labels of the columns for coefficient estimates and feature. Okay, and kind of, transpose the order. And then we're going to construct this data frame with this, 3 columns, which is the feature, the coefficient estimates, and the absolute value. Why do we have to use the absolute value? Is to give it an order, because those coefficients could be positive or could be negative. So with the absolute value, the absolute estimates, then we can order it. And that's what I'm doing here. Sort values by that absolute coefficient, and then doing ascending false, which is a descending order. But here, I mean, we can see more or less, which some of these predictors are. But if we do a plot, a visualization with Seaborn, then it's easier to follow this, okay? And now we have the top 10 predictors that are contributing to this, the outcome to this model. What do you see here? from these predictors? What is the number 1, number 2, number 3, number 4? Okay. Amounts. That's right. Okay. All those predictors were engineered from the amount transaction. But as you can see, the amount transaction by itself doesn't appear here. What it appears here is the log amount, which has a positive, a positive estimate, a positive weight to the outcome. In other words, the log amount, when it increases the possibility that that transaction, the probability that that transaction is going to be fraudulent. But interestingly, we engineer also divided that amount, amount feature, we divided into buckets, okay, in our feature engineering. And we divided into buckets to see if there was a relationship between certain groups of amounts. And as you can see, these certain groups of amounts tend to go the other direction, okay? So when the transaction increases, then the probability of the outcome, if it's fraud or not, decreases. And that is something really interesting, right? Because in the whole, on the log amount, you see that it increases the possibility when it increases the value of the transaction in the credit card. But here, the groups are saying that within each group of that amount transaction, then there's a opposite effect. Very interesting. Also, look at this, CC number. CC number, that's the credit card number. And it also has an importance, okay, apart from the transactions. So that could tell us that there are some credit card numbers that are more prone to generate fraudulent transactions than others, okay? And that's something that you have to, to kind of, research there. And then some categories, and we, what expected that. I didn't expect the grocery point of sale, okay? I expected more the net transactions, but that's what the model says so far, okay? And remember, this is a baseline. We're getting just a first glimpse at what, our predictors are trying to tell us, okay, from this model. And then we have at the last of the 10, we have the amount, the original predictor. We give us, a clue of the importance of the feature engineering. Okay, now let's discuss a little bit about the ROC curve. And the ROC curve is a very important measure because it tells us how well the model is capturing, those, apart from the true positive and true negatives, also capturing the false negatives and false positives. In other words, trying to minimize and try to augment that the true positives and true negatives, which are the correct outcomes. So what the ROC curve does is that you get the false positive rate, okay? And you get what is called the true positive rate, which is 1 minus the false negative rate, the FNR, okay? So you do these numbers, and what the visualization is telling us is that when the model hugs this axis, to the left and to the upper end, okay, it hugs the one axis. That means that as the model approaches those axes, it's a better model. If it is not hugging those axes, then it's not a great model. And if we have something near this diagonal line, which is 0.5, which is the toss of a coin, that means that the model is as good as a random chance. Okay, in other words, this is the worst outcome, the 0.5. So you want your model to go to those axes. So let's see how our logistic regression is doing. Okay, for that we need the probabilities, and this is going to calculate the probabilities. I'm not going too much into detail, but these are the the coding there. And then we get this, and this is for, right, for the test. Okay, the one for the test, the white pred. Okay, and you see that the model is doing very well here, right? Okay, hugging that line, etc. But then something happens that it kind of flattens out. Okay, and it stays away from this axis. So what I can tell you is that from the confusion matrix, the problem is here, okay, with the false positive and false negatives. Here, the model is doing pretty well, right? Okay, here, because it's just predicting, okay, I have no problem predicting when a transaction is not fraudulent. But I have a big problem when a transaction is fraudulent and the prediction, I cannot catch it. Okay, it's around 67%. So we have to do some adjustments here to try to minimize both, but minimize this one, okay? Because remember, what would be the cost of your organization for a bank, for example, if you have fraudulent transaction, but you're not catching it, okay? You get insurance costs, because sometimes you have to, reimburse that. Then you get an angry customer. Okay, probably you lose the customer and so far. So the ramifications of this number are pretty serious. Okay. Okay, so far so good. Tell me.
We're doing good, Ricardo. We've got about 3 minutes left before the top of the hour.
Okay, so let's do something to wrap this up. So remember that the model, okay? Remember that the model that we use is the default model, okay? And it's not doing that bad. In fact, it surprised me. I thought it was going to be, worse. Okay, but let's try to see if we can change some of the parameters. And some of the parameters could help, get a better model. Could, okay? I'm not, let's see what happens. So we're going to use, instead of a penalty, the default is the penalty, what is called an L2, which is what is called a regularization of the predictors. When they have, the issue of multicollinearity, they tend to be penalized. So we're going to use the elastic net, which is a combination of what is called rich regression and lasso regression, okay, which are two of the traditional regularization methods. We're going to use a mix. This is the L1 ratio. We have to do a mix in the elastic net of 50% lasso, 50% rich. And then we're going to also activate this class weight parameter to balance. And what it is going to do is that also is going to alter the weights in the model to try to compensate for that imbalance that we have in the target. Okay, so let's run this. This one is going to is going to spend some time. Okay. Okay, let me see if the run doesn't last too long. I think it was about 2 minutes. So let's see. Okay. If you have any questions, now is the time. Until we get the fitted model, because then we're just going to run through. Okay, and try to see if our model is making an improvement or not. In fact, most of these parameters, what you do is that you tune them. Okay, so you run what is called a cross-validation method, and then you start tuning them. You give it a range of options, and then you start tuning. And using that metric, right, the stochastic gradient descent, you'll see that then a mixture of these parameters will give you, the top performer. Okay.
And I'll just, while we have a few seconds here while it's running,
Sure.
I'll just reiterate. So if you want to go and play with this code directly, you've got it in the Google Drive link. There's a link to this notebook out there, and you can use it.
Sorry, I didn't understand.
In Colab.
Sorry.
I think somebody's Google Assistant.
Somebody activated the Google, yeah.
Sorry.
Here we go.
But just
Okay,
a
so
reminder, check those links, both the GitHub repo and the Google Drive link should be able to get to the code that's this notebook directly. And
okay, so we
I
have the model.
highlight, yeah.
Okay, so we have the model fitted. Let me see if we can do a quick run to see, more or less. Okay, so according to this, the score of the ROC-AUC for the test, for the test portion of the trained data set is 0.9121. So that seems like an improvement, right? But let's see the confusion matrix. And in the confusion matrix, you will see that, yeah, it minimized that problem that we had of fraudulent transaction not catch, but then it went all the way, on the other side. So now what we have here is that there's some transactions that are legit, but the model is telling us that they're not, that they're fraudulent. And that also creates problems too. Okay. So, it went the other way, the other way here. So we need a more balanced, approach here. Okay. This is the confusion matrix. Okay, visualized. All right, let's see if we can run this quickly. Okay. All right. So yeah, we're doing better in that, that actual is one, that is not, is not happening, right? That we're catching those transactions. And you can see that from this number, 0.32, we jump to 90, the true negatives, right? So the model is getting better. It's getting better. The problem is that now our weakness is in the transactions that are not fraudulent, but the model is predicting that it's fraudulent. So there has to be some balance here, okay, between these two. It's going the other way. So let's do this. Okay, let's see if our coefficients, the importance, the estimates are the same. And there has been some difference here, okay? Because now the amount is the one, not the log amount, okay, or the bin amounts, is the amount, the real feature now is doing the first one, is has the greatest estimate. And then we have another bin that is telling us that it's going to the positive side, and then the CC numbers. So basically, those are bubbling up into the importance, the variable importance, okay? Then quickly, let's run the ROC curve, right? To see how well our model is doing. Okay, let's see. Show me. Okay, so as you can see, this one, seems to be a better model, right? It's hugging those axes, the one on the left, the one upper, the one axis, right? But let's do the true test, which is with the new data, that test data that we are separating from all this process, the new data. So let's do this, okay? And now we have 0.67, still a gap, right, between the training and the test set, okay? But it's going the right direction. We still have the same problem, okay, that we're capturing those fraudulent transactions, we're capturing them. But now, we have that problem of the ones that are not fraudulent and the model says it's fraudulent. So let's see the ROC curve once more with the test, with that new test data. And as you can see, it has a better shape, okay? Still, there's a gap here, that we're not covering, which is the one related to those, false positives, okay? So basically, that's it, okay? Any questions, any comments? So this is a quick introduction to SciKit Learn. Okay, we have a question. Let me see. How do I know which penalty regularization should be used? Do we need to always train the model with different estimates to compare the results? Yes. What we do is that we do a process called hyperparameter tuning. And what we do is that we cross-validate. In other words, we divide that training set, instead of in 2 chunks, we divide it in several chunks. Usually, the traditional number that I use is 10 chunks of train and test, train and test, train and test. Then we prepare kind of a grid, okay, to run, different models changing this hyperparameter. And in the regularization, for example, you can change it to, let's say, from very small to very large, okay, very large. And then usually the result of the cross-validation, what it's going to give you is the best performing models with this set of parameters. So you use those set of parameters and then run the model with the test data to validate that, yeah, there's no overfitting, there's no, a big gap, and we are satisfied with that model. So for next session, okay, what we're going to do is put this in overdrive, and we're going to use PyCaret, because PyCaret sits on top of SciKit Learn, and what it does is that runs all the models that the SciKit Learn library can offer. It runs all of them, okay? And we then can choose which is the model that is performing the best, and then hone on it. Do the hyper tuning, do the hyper tuning, etc. And then we are going to be ready with the best model that we can achieve to then deploy it. All right. Okay. Very good.
Okay. We're a few minutes over, but hopefully everybody got a great session out of this today. I know there's a lot covered. It's tough to cram some of these into an hour, but great job, Ricardo. Appreciate that. And we're planning right now for our next session mid-December, trying to fit one more in before the end of the year, the second week of December, because we know after that the holidays get all crazy, and everybody will be off to wherever to spend time with family and friends. So we hope to see you around December 13th or 15th. I forget the exact date, right around there.
For those celebrating the holidays, happy Thanksgiving,